here's going to be our door into this topic. Okay? This is going to be our door. I want you to recall when we did sum and difference of cubes. Okay? I know that was a little while ago, but the whole intention of us spending a bit of time on the beginning of the year was to cement it in our heads, right? And sort of be the pathway to this next topic, okay? So, help me out. Before we do all the signs, what are the actual algebraic pieces that I'm going to fit in there? X, and then Y. So that's an X. X squared, X, Y, Y squared. Good, okay. I've got the same algebraic pieces for both sum and difference, right? And then all I need to do is vary the signs with SOAP. Same, opposite, always positive, okay? Same, opposite, always positive. Yep. Same, opposite, always positive. Fantastic, okay. And where we're going to go from here is something subtly different and kind of in reverse, right? So what we have here is something that is expanded and we factorized. Expansion to factorization, okay? It just so happens that the expansions of this very messy thing turns out to be a very nice and neat expansion, okay? We're going to now go in the opposite direction. What if we have something like this, okay? Now this is factorized, and we're going the other way into an expansion, okay? Now, we are going to get to the point where we can quote out this result, okay? But before we get there, well, before we get to that, I just have to do it by hand, don't I? Okay? Now, there are some steps I can make this easier for me, right? This is x plus y times x plus y times x plus y, right? Well, if I take one of them out, one of them will be a square, okay? And I'm very good at squares. We're really good at squares, right? So this is going to be x plus y, and I'm just going to quote my result for a perfect square, which is x squared, 2xy, y squared. So far, so good. And now I'm going to expand out, right? I'm going to continue. So I'll do my x's first, everything by x, and then everything by y. This time we actually are using the distributive law, okay? I've got an x cubed there. What's your indices? 2x squared y, x, y squared. Okay, is that all right? Of course I could write that as y squared x, but I'm going to try and keep things consistent. It'll make it easier for me to, number one, see the logic behind it, and number two, collect the like terms in a second. Done the x's, let's do the y's. What shall I write? X squared y?
Plus 2x y squared.
Good. And I finish with a y cubed. So far, so good. All right. I can see some like terms. Help me pick them out. I've got an x squared. I've got two x squared y's there. And I've got one there. Yep, so I'm going to have 3. And in a similar way, I've got an xy squared there. And I have 2 xy squareds there. That's it. That's all the like terms there are. Okay. So what I have is x cubed plus 3x squared y plus 3xy squared plus y cubed. Okay, this is good. A couple of things to notice here, right? Notice just like this was structured, this is supremely structured, right? Can you see, let's highlight it, right? I've written it in such a way, I've written it alphabetically, so that you can see the powers of x decreasing. There's an x to the naught there. We don't need to write it. And in exactly the same way, but in reverse, you see the y's increasing, right? So you have this sort of symmetry there, but that's not the only thing. You also have these coefficients that are also similar, right? Okay, now look at the coefficients. They're kind of suspicious, right? If you recognize this, you're like 1, 3, 3, 1. It's kind of sus. This was x squared, right? 1, 2, 1. That's what you get from x squared. What do you get from? Let's climb back up the ladder, right? There's x squared, x plus y squared. There's x plus y all cubed. What would be, go this way, x plus y to the, what's the previous power? It'd be, previous one would be 1, right? Which is just 1x plus 1y. And I can go back up one more time, can't I? Just x plus y to the power of 0, which of course is always 1. So what am I seeing? I'm seeing a 1, and then I'm seeing 1, 1, and then I'm seeing 1, 2, 1, and then I'm seeing 1, 3, 3, 1, and you can bet your bottom dollar
1, 4, 6.
that if I take this guy, what are we going to expect? Alright, so watch the pattern first. These powers, right, these high powers, they match what I raised it to. So I'm going to start with an x to the 4. Right? I'm going to leave off the coefficients for a second. The next one will be an x cubed, then a y. The next one will be an x squared and then a y squared. You can see what the powers are doing, right? One's going up, one's going down. I'll have one x left here, and then a y cubed, and then an end with a 4. So you see the symmetry. And just like I had this 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. The coefficients I'm getting here are 1, 4, 6, 4, 1. Okay, now, we've identified a pattern. Mathematics is so much about patterns. And we're just kind of guessing that this is true. We have some reasonable evidence so far that it's true, right? But it's nowhere near a proof. We're not going to get there yet. The maths is a little more involved, okay? But this structure, right? The open question I want to put on your minds is, why should this, which is just made by addition, that's how you make it, right? Why should this have anything to do with this, okay? Now, we will get to an answer to that question, right? But I simply pose to you now, right? Because we are not the first people to recognize that this triangle is important, okay? Even Pascal wasn't the first person to notice that it was important. It's just he was the one who popularized it, so his name got attached to it, okay? Why should this process, which even a very, very young child, addition? You could be like, my daughter is 6 and she can add numbers that big, okay? So a 6-year-old can make that. What does it have to do with this?